The objective of this lab was to observe the motion and use observational data of the star to infer the mass of the black hole. I did this by approximating changes in momentum data and finding the net force acting on the system. The main result is that the mass of the black hole is 5.57 times 10 to the 31 kilograms. By applying Newton's gravitational force principle, which is F-grav on the second object by the first object equals negative g times m1 times m2 times r hat divided by magnitude squared, I was able to determine the mass of the black hole. Then, through my observations, I was able to see the connections between the different FNet components and dp dt components. So to set up my model, I specified the mass of the star, which was given a MOPA sign, the time step, the black hole position, and here in the code, you can see the mass delta t, and then we started at time t equals 0. And then here is how the computational model predicts the mass of the black hole. For this loop, I use the momentum principle saying that dp dt equals Fnet, and then the different force components. So Fnet equals Fnet perpendicular plus Fnet parallel. From this, I can set Fnet parallel equal to dp dt parallel and Fnet perpendicular equals dp dt perpendicular. And you can see that here. And also I labeled the arrows for Fnet perpendicular, Fnet parallel, and the overall net force. Note that the arrow scale needs to be small because the arrow scale is like a correction factor, and it's as if we're trying to compare newtons to meters. So here I specified the hole position, and then here I found the mass of the hole, and I did this by simply rearranging the equation for Newton's law of gravitational force. So if we run this code, we see the curving motion, and we just saw the 3 arrows for Fnet, F parallel, and F perpendicular. For the model analysis, we already know that Fnet equals Fnet perpendicular plus Fnet parallel, and the initial momentum is magnitude of p times p hat. To find the rate of change, we find that dp dt equals d of magnitude of p times dt times p hat plus d of p hat times dt times the magnitude of p. And we already know that dp dt equals dp dt perpendicular plus dp dt parallel. All of this is accounted for in the code. So the main difference between Fnet and dp dt is that the change in momentum can be observed, but the change in force cannot be observed. For the parallel components, they show the magnitude of motion on the axis parallel to motion. So dp dt parallel is the observed magnitude of motion. Fnet parallel is the sum of all forces on the axis parallel to motion, and this causes dp dt parallel, and it's calculated from dp dt parallel. And the perpendicular components show the direction of motion. So dp dt perpendicular is the observed change in momentum, and Fnet perpendicular is the sum of all forces on the axis perpendicular to motion. It determines dp dt perpendicular and is calculated from dp dt perpendicular. For the what if question, no, we cannot find a value for the mass that is different from the original mass because of the gravitational force principle, which is F net equals negative g times m1 times m2 times r hat divided by magnitude squared. And if the motion of the star is unchanging, that means that the data points are still the same, then this means that there is no alternate F grav available to calculate a new mass of the black hole. The trajectory would change and we would not get the same curve if the mass were different from the original.